What's up, fellas? It's your boy Andy. Huh. I hope everything's alright. Tell me please if you can hear me and see me, because I get a black screen here and I don't really like it. Tell me if everything is alright, please. Oh, alright. I think now you can see me. Alright, cool. So, let's start this. What's up, guys? How you doing? Kind of a bad news, huh? This Codeforces Round is also going to be unrated, but I hope you had your fun solving the problems, right? First of all, call to action, hit all the buttons that you see in your screen, like this kind of lives, subscribe to Algopedia, and yeah, support the channel. Let's do some epic stuff together, right? But for this, you have to support it. If you haven't subscribed yet, come on, it's not that hard. Just press that button and invite all your quarantine programmers buddies to also subscribe. So enough with the all right, you can hear me, perfect. Enough with that marketing stuff, and let's get into the round. So yeah, it was a div 2 round. We had problems from A to F, but unfortunately we couldn't know how many people solved the problems, what problems and stuff, right? So yeah, I kind of lost my enthusiasm after I waited like 3 minutes to solve problem, to see if I've actually got right the problem A. I was like, coded problem A, bam, submitted, and then I was trying to read problem B, but I couldn't concentrate because I was like always switching tabs, like I had problem A in one tab and problem B in the other tab, and I was like, once in 10 seconds I was like looking if everything's alright on problem A. So yeah. In which company do you work? That's a nice question. It's a surprise for you. I'm gonna tell you where I work and how I got there, because it was quite of a journey. How I prepared, how I considered preparing for the coding interviews and stuff, but that is for another series of videos. But I'll do that because it's an interesting story and you should know it. But first, yeah, so some of you want to start with C. All right, let's do this. Hilbert Hotel. Cool. I really love this question. It's kind of a geeky maths question, but it's actually pretty nice. So I think Hilbert's Hotel is from something like Hilbert's curve or some function, I don't know. This guy Hilbert was some math guy who I think had some theory about the infinite numbers or something. If you know, you can write in the comments. So yeah, but anyways, let's read the statement. So as you probably know, you are given this hotel and basically you have an infinite number of rooms from minus infinite to plus infinite, and there is exactly one person staying in each of these rooms. Cool. Everything not normal for a hotel right now. But the interesting thing is that you are given an array, right? Which is called A and has n integers. And what happens is that for each number k, so for each room which has number k, of course, from minus infinite to plus infinite, the guy who was staying in that room, number k, is now going to be asked to leave that room and go to room number k plus a of k modulo n. And this modulo is, yeah, they give us some definition for this modulo, but we are gonna get into it. So let's see how I thought about this problem. Let's see, I don't know how many of you solved this problem, I can't see, but yeah. So let's take some examples first, right? I have basically read this problem, and of course, first thing I know, it's some math stuff. And basically, when you're reading on Codeforces a problem that's about math, you usually have to get your pen and paper close to you. I didn't do that. I took my risk. And it turned out I can solve it like only thinking about it, not writing anything. So let's see. Let's take some examples. What I did is I took a look at these examples and let's take the third one, which is quite interesting. So we have 4 elements, right? So we are given 4 elements, 4, they are not rooms, I don't know, 4 elements, n equals 4, whatever. So n equals 4, and the array A is 5, right? 5, 5, and I think the last element was 1. I'm not pretty sure. Was it? Yeah, it was 1. So let's see what happens here. First of all, let's index these integers, right? 0, 1, 2, and 3. And let's try to imagine the rooms of our hotel. What we have here is, I'm gonna use my drawing skills. So, minus infinite. Next room, minus infinite plus 1. And so on and so forth. Room number 0, 0. Room number 1, and so on and so forth. Until, of course, room number infinite. And don't ask me how I know this is room number infinite, because I don't. But let's imagine we can get in front of room number infinite or minus infinite, right? If we had superpowers or something. So basically, let's imagine all the rooms in our hotel, right? Lined in a row. Cool. And let's see what happens. Well, as we said, the guy in room number K is asked to leave the room and move to K plus A of, I think it was, yeah, K modulo N. Cool. So, let's see what I did here. I have taken a look at this formula, and I see 3, let's say, letters, which is K, A, and N. Cool. So, what I basically see here is some integer K, which is between minus infinite and infinite, and some integer A of K modulo N, which is from, of course, the input array. So I'm thinking like this. Alright, man, I have 2 integers. One of them is infinite, could be anything. I can't possibly fix the K or something like that, right? So I really have to do something with this A. So what I basically did is that, because K can take an infinite of possible values, I knew that A of K modulo N can take only N possible values, right? Because there are N values in this array. So there are N possible values. So what did I do? I didn't fix K, because no one can do that, but I have fixed K modulo N. I have fixed each and every K modulo N. Of course, this is between 0 and N minus 1. That's the first thing I know I have to do. And let's start from the beginning. Let's take the case in which K modulo N is equal to 0. Let me erase this down here and see what happens. What's going to happen on scenario number 1? K modulo N equals 0. Well, first of all, let's take a look at A of 0, which is 5. Alright. What does the problem tell us? That the guy in each and every number K, which is now a multiple of N, right? Because we have set this reminder, we know it right now. So what are the possible values for K? 0, which is this room, then could be n. So let's say here we have room number n, could be 2 cross n. Here we have room number 2 cross n, and so on and so forth, of course, infinite values here. And also their negative versions, right? Which is minus 2 cross n, minus 4 cross n, and so on and so forth, right? So here I have some doors, some rooms on my left too, minus 2 cross n, and so on and so forth. What happens is that I can imagine that all these guys are taken out of these rooms and they are shifted by 5, right? That's all. They are just shifted by 5, right? Plus 5, plus 5, and so on and so forth. All right, this hotel is infinite, but there is actually one thing which we can mathematically notice about these numbers. What happens is that we kind of rebind these numbers. What used to be 0 is now 5. What used to be n is now n plus 5, and so on and so forth. So what I did is the following thing. If I can imagine an array of infinite numbers from minus infinite to infinite, and every value in this array is 1 because there is one guy there on that position, which we will call the array of rooms, alright? So the array of rooms was something like this: minus infinite plus 1, dot, 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 0, 1, dot, 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 infinite. Each value on this or in this array is 1. When k modulo n is 0, I literally take all these positions, position 0, position n, position minus n, position 2 cross n, position minus 2 cross n somewhere here. And all I do is take that 1 here and move it to that position plus 5 for this example. So I basically asked myself the following thing. How can I make sure, or how can I check if after performing all these moves, basically, right, subtracting 1 from here and increasing 1 here, yes, how can I make sure that the new array, let's call it, those are free of O's actually, let's call it, I don't know, rooms prime. The new array rooms prime also has only values of 1. I have to make sure about this. So basically, I have to make sure that there isn't any position P, right, where there are two different positions x and y that are going to be basically to get here, right? So I have to make sure that there aren't two different rooms x and y that are going to be binded to the same number p. Basically, I have to make sure that this function, which takes my people from their rooms and move it to other rooms, is, how do you call it? I can think about the term, bijective or something. I think that's the term for it, yeah. So there are not any two different values which are going to be equal. So, having thought about all this, let's get back to this k modulo n. Now everything is gonna be clear, because on this example, on this case, on this scenario, when k modulo n is 0, what happens is that each number, each position from this array, which is a multiple of n, now is not going to be anymore a multiple of n, but its remainder modulo n is going to be 5. So, for this scenario, where, let's say here, right, k modulo n is 0, basically, each and every number which modulo n was 0, right, so it was a multiple of n, now, from multiple of n, let's say something like, I don't know, d crossed n, is now d crossed n plus a of 0, which is this value. So if that number modulo n was 0, after performing this, the new number modulo n, guess what, should be a0. Well, a0, of course, modulo n. So the whole thing that happens here is that one remainder becomes another. What we have to imagine, instead of that infinite array of rooms, is that these rooms are grouped by the remainder of their index, their number, modulo n, right? So on that infinity of numbers, I'm going to have the numbers which modulo n have remainder 0, the ones which give remainder 1, remainder 2, and so on and so forth, and lastly, all the numbers from minus infinite to infinite which modulo n give remainder n minus 1. Of course, there are an infinity of numbers in each of these n groups, but that doesn't matter. When I took a of 0, each and every number of remainder 0 became now a number of remainder a0 modulo n. So this 0 becomes a0 modulo n. Then, what about remainder 1? Well, each number which was something like, let's write here 1, each number which was something like d crossed n plus 1, so gave remainder 1, now is going to be increased by a of 1. So is d crossed n plus a of 1 plus 1. If this remainder was 1, the new remainder is a1 plus 1 and everything modulo n. Right? For 2, what happens? Exactly the same thing. So, remainder 2 will become a of 2 plus 2 modulo n. And you've got a whole idea, right? So, what happens is that for each and every remainder r between 0 and n minus 1, now this is going to be transformed, as you've seen, into r plus a of r, everything modulo n. What did we notice, or what what did we agree that we will have to check? Remember, we said that there shouldn't be two rooms x different than y, such that after the transformation they became equal. And as we've seen, because we transform the numbers grouped by reminders, this can happen if and only if the remainder of x modulo n and the remainder of y modulo n, if these two are different, of course their reminders are going to be different. If these two reminders, after applying the transformation for all the reminders, become now the same reminder, which is z modulo n. So all we have to do is that each of these numbers, r plus a of r modulo n, are also going to be different. All the values from 0 to n minus 1, right? So we have basically started from the permutation of all the numbers from 0 to n minus 1 in this order, and we will obtain another permutation, right? Based on the formula r plus a of r modulo n. And basically we will obtain an array, and if this array is a permutation, then everything is fine. Because as I've told you, if this is a permutation, this means that each two different reminders after the transformation are still different, right? So if r1 and r2 were different from this permutation, and after the transformation they are still different, this means that those numbers x and y, which were x in group R1 and y in group R2, what happens? After they are transformed, if their reminders modulo n are different, of course the numbers are going to be also different. And that's it. This is how you solve this problem. You don't think about the infinite possible values of the room numbers, but you think about their finite possible reminders modulo n. And in this way, you have something finite, right? So you can iterate through those elements. So what I basically did here is the same thing, is the following thing. I've basically have iterated through the whole array, A. And I had something like a hash table, right? Hash table, unordered map, unordered set, frequency array, vector from STL, it's really your choice. Let's say it's a hash table, just for the sake of it. I've had a hash table, and for each and every element from this array, I simply checked if that element a of I plus I modulo n, if this value hasn't been encountered, or if this value is not part of my hash table. If it's not, that's cool, insert it into the hash table and continue. If it is part, then simply return -1. And that was it. Just one thing. I have had one problem, and I don't really know if you encountered it too, but I have had one problem. Fast. How did you solve D? Yes, D. And yeah, we're gonna get to that D. And yeah, basically the problem was when these numbers are negative. Because if these numbers are negative, the value ai plus I, everything modulo n, is not going to be correctly computed. So what I did basically is that if this number is negative, I have increased it by a value like 10 at power 9 crust n. So I make sure that this final value is positive, and also the remainder of this value is equal to the remainder of this value modulo n, right? Be very careful here, because if you take something like minus 2 modulo 10, you should get 8 for this problem, but you will get minus 2, which is a problem. But if you take this minus 2 and increase it by something big enough, so this becomes 8, which is greater than 0, then the remainder modulo 10 is 8, which is indeed the great one. So the problem that I had, and I solved it quickly, is to increase this number by something big enough so it becomes positive. And that's it. All about the reminders. Cool. Can I suggest a problem? Still have time? I don't know, man. Let's hope we have time, but I don't really think so. And yeah. Let me see a little bit the... Oh, I have Cristiano Ronaldo here. I think Cristiano Ronaldo is not written with CH, but it's your name. Maybe you know better, right? Alright, cool. Let's see, guys. It looks like problem D didn't work. Yeah, it didn't work. Huh, wrong answer on pretest 2. That's actually funny, but why on pretest 2? That doesn't make any sense because it has worked. Really? My output is 1 and expected minus 1. Okay, that's weird. I know that anyways, doesn't matter. Alright, let's jump into solving D, and then I'll figure out why that happened. Yeah, D was actually a very cool problem. Very, very cool problem. And yeah, you probably know the statement already, so I won't bore you to death. Let's see here. B, please. Yeah, we're gonna get there too. So, alright, cool. Basically, what you had here is some grid of n rows and m columns, and each cell in this grid is either black or white, right? So you have this grid, black and white, and you have something that are called, I think, monopole magnets, right? Which there are magnets which are only of one pole, which can be north or south. And what we had to do here is to find a way of placing how many magnets we want in whatever the cell. We have to choose that, we get to choose that, such that there is at least one south magnet in every row and every column. If a cell is colored in black, then it is possible for a north magnet to occupy this cell after some sequence of operations, and if it's white, it's impossible to do that. And the sequence of operation, as you know from the statement, is taking that magnet and choosing a south magnet and using that magnet so that we actually move our north magnet, right? So, are we ready? Should we do that? I really love when the number of the guys watching gets increased super quick when I switch to another problem. Like, you're listening and you're like, next problem, all right, cool, I should get in. That's actually funny. That's a good way. It's smart. I would do that too if I were you. So yeah, all right, cool. So you basically know the statement, right? No more need to explain that. Let's jump into solving this. Cool. So let's see. Again, in the statement, I am competing here, right? And I've read the statement. What's in my mind? Well, first of all, after I finally understood the statement, I'm like, so the problem asks me to minimize the number of north magnets, but doesn't care about the south magnets. All right. The only thing that I have to do is to make sure I have at least one south magnet in every row and every column. First thing that I think of is, why not have a south magnet in each and every possible cell? Like, if I don't care about their number and I use them in order to move the north magnets, why don't I literally place a south magnet in each and every cell? Well, because you have the third restriction. And if you did that, you would have some white cells in which some north magnet could actually get there, right? So, alright, I was like, alright, that's not that smart to place a south magnet in each and every cell. Let's take a look at these examples. This problem is a perfect example of how powerful it actually is to look at the examples. And the author did a very, very great job, let's say, for us, and helped us a lot that he drew these examples. Because I literally have to look on the first example. What do I see? Alright, north magnet here, south, 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 south. Alright. This actually doesn't tell me anything special, just that I have a south magnet everywhere and it's possible. Cool. Then, second example. What do I see? Well, I see that that's not possible. Alright, nothing special. But when I've taken a look at the third example, an idea struck to my mind. What did I notice here is that I have a north magnet for each and every island, right? These two look like some islands, and I have a north magnet in each and every of these islands. So after taking a look at this example, I immediately thought about islands. Then, what I did is that I have an island, like this one. Cool. Another observation is that if I take an island, will I ever be able to have a north magnet outside of that island reach that island? I'll never do that. Let's say this is the island, right? And I had some north magnet here in this cell, or here, for example here. To take this north magnet and have it to visit this island, I have to go through at least one white cell. So the first observation of my solution was that for each and every different island, I'm gonna need at least one magnet in that island. This helps me a lot right here, because after noticing this, I already know the lower bound of the answer. If for each and every different island I have to place at least one north magnet inside the island, the total number of north magnets is at least the number of islands. Cool. Then immediately I thought, it probably is indeed the number of islands. But I haven't proven that. So I'm being a responsible coder, and I try to prove my statements before getting to coding this. I knew that the answer is the number of islands, and that is the answer indeed. I'm sure of that. But I've spent 10 more minutes just to prove it. Because if I didn't, I had no clue about what is wrong with my solution. And that would have lost me hours from the contest, not only these 10 minutes, right? So, I don't know about you all, but I really suggest you to prove all the things that you are going to code. That could be a quote right there, something, write it down. Prove all the things that you are going to code. That's pretty cool. All right, so how do I prove this? How do I prove that the answer is the number of islands? I started thinking about this. And then it struck to my mind that, wait a minute, if the answer is the number of islands, in the second example, the answer should be 1, but it's -1. So I should think about when it's impossible to do this. If it's impossible to do this, I return -1. If it's not impossible, I return the number of islands. Alright, perfect. So when is it impossible to do this? Well, this is not that intuitive. But again, the author was very helpful here with this drawing. Let's take a look at this grid. Right? What is the problem here? Well, the problem is that if we place a north magnet here, like we do, and have a south magnet here, I can basically use this south magnet to move on this cell. So it's impossible. If I haven't had this magnet here, I wouldn't be able to get to this cell, like in this example. So the problem is that this is a black cell, this is a black cell, and between them I have at least one white cell. That's it. I immediately knew that I am going to return -1 if there are 3 cells on the same row or the same column that are first one black, then white, then another black. So basically, if there is some row or column where there is at least one white cell between 2 black cells, I'm going to return -1. Makes sense, right? Well, yeah. Looking at this example, it makes. But again, I wanted to prove it. So how did I prove it? Well, let's see. How did I prove that if I have black cell, let's say this is another black one, let's say this is another black one, this is a white one, and again a white one maybe, who knows, and again these are black ones, right? So how did I prove this is wrong? Well, I thought about this. Let's take this cell for example, right? If this is a black cell, that means that at some point some north magnet needs to get there, right? Let's change the color. At some point of time, I'm gonna have a north magnet that would literally be in that cell. Otherwise, the second constraint is not satisfied. The second constraint says clearly, you have to be able to reach this cell with at least one north magnet. So this north magnet at some moment of time would be here. But if it would be here, let's think about this. It also shouldn't be able to reach these 2 cells because they are white. So what happens is that it should be able to reach these cells, but not these ones. But when a magnet here, when will a magnet from here reach one of these cells? When I have some magnet in these cells. So if there exists some south magnet in one of these cells, that north magnet that reaches this cell is also going to be able to reach these cells. So what I notice here is that for each and every black cell, the first white cell to the right, and the same is true for left, but if I see what is the first white cell to its right, then from that cell to all the row, like starting from that cell to each and every cell from this row on its right, I'm not able to have any magnet here. Because as I said, if I had a magnet here, this north magnet who will be here sometime would also get here. And yes, the same is perfectly true for left, right? If I have white cells here and that magnet reaches this cell, I'm not able to have any magnet here, no magnet here, because if it was a magnet there, I could have chosen it and then got to these cells. So what I noticed is that on each row and column, it's tiring to switch these colors on and off. So for each row or column, doesn't matter, if there is some black cell somewhere, of course, the black cells to its right, which are neighboring, are okay. The black cells to its left, which are neighbors, are okay, right? But from the first white cell on its right and the first white cell to its left, I won't have any magnet there. Or in other words, for each row or column, I can have a magnet only in the black adjacent cells. And more, I'm not able to have two, basically, how should I call them? Let's call them two sets of consecutive cells from that row or column which are black, only one, right? So I won't be able to somewhere here in the right have another one full of black cells, right? Because of course, the same thing holds true. If I chose this sequence, I'm not able to have any magnet there. But if I chose this one, I'm not able to have any magnet there. So I won't be able to have any magnet anywhere on this row. And if I can't have a south magnet on a row, that's an impossible scenario. So the final observation, and why I did all of this, is that on each row and column, you are allowed to have at most one set of consecutive cells which are black. If you have two of them, it's over, -1. After I knew all of this, I said to myself the following thing. Alright, I'm gonna check for each row and column this property. If it doesn't hold, -1. If it holds, can I now return the number of islands? And yes, now I do. Why is that? Let's take again another look at the statement. Are you with me? Yeah, some of you are. Alright, cool. Then, here, alright? Am I now able to return the number of islands? Yes, I am. And why is that? Because for each and every island like this, what I'm gonna do is have south magnets placed on its borders, or in in its extreme cells, let's say. And because there are no multiple sequences of black cells on the same row or column, that is going to be fine, right? So let's say if I had some grid which looked like this, I don't know, maybe I had an island here. This is some kind of island, right? This is some kind of island, alright, this is an island, right? There are only black cells here. What I'll do is that I'm gonna have these south magnets on the extreme cells. Let's change the color to red. I'm gonna have south magnet here, south magnet here, right? South magnet here, probably two south magnets here, 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 and you got the whole idea. And everything is fine, right? So here also I won't have multiple, or I can maybe. Anyways, and the whole idea is that for each and every island I will have the south magnets here, right, on its extreme cells or border cells, let's call them. And I'm gonna have exactly one north magnet placed inside the island. Because those south magnets are on the extreme cells, they will help me to move wherever I want, so everything is fine. And also, I'm not going to get out of the island. And why is that? Because if, let's say, I have this island and I have that magnet inside, let's suppose I will be able somehow to get out and maybe get with the magnet here. In order to reach the magnet, to reach these cells, there has to be some south magnet here, right? Some south magnet here. But it's not going to be. Why? Because this is a black cells, and as we've seen, we won't have any magnets here. This is what I've proven previously. So that's it basically. The whole problem resolves to this. Check for each row and column if there is at most one consecutive subsequence of black cells. And if it does, the answer is the number of islands, because you are placing exactly one magnet inside each island and the south magnets on the extreme cells. And in this way I can explore the whole island without ever getting outside the island, because if I would, that's a contradiction right there, because I have earlier checked that I won't have any black cells on the same row or column. And that's it basically. The whole problem is counting the number of islands in a grid, which is a classic problem. I won't explain the whole algorithm here, but it's just a DFS, alright? You'll have a recursive function to go through the grid and count all those things. And that's it. That is exactly it. Hope you all got it, guys. Create cards reg to use all n cards. I don't know what you're talking about. Probably another problem. Yeah, and this was problem D, right? So just doing this. Cool. I don't know about D. I'm gonna take a look about what happens. Oh, this B was simple. I think you probably got it, but this is probably simple. Yeah, be very careful about the long, right? Because the formula here, if you take a look about it, it's something like the Gauss sum, I guess. Let's see. I think it's the Gauss sum or something, right? Height 1 is... It's not the Gauss sum. Alright, so for height h, let's say, let's notice that you have... How many triangles do you have? Well, you have one triangle here on top, then two triangles, three triangles, and so on and so forth. And on the last layer of triangles, the only difference is that those triangles have one edge in minus, right? So the answer is the number of triangles, which is 1 plus 2 plus 3 plus dot 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 plus h. This is the number of triangles. Each triangle has 3 edges, but the triangles which are here on the last layer, on the bottom layer, have 1 in minus. So we will subtract h. This formula is of course 3 crossed h plus 1 divided by 2 minus h, which I think you can write as I think 3h squared, yeah, 3h squared minus h divided by 2, which is 3 divided by 2 h minus 1. Yeah, all right. So you have this formula, right? As the problem suggests, you're going to find the greatest h such that this number is less or equal than n. The beautiful thing about this is that you have this product, h crossed h minus 1, which is almost equal to h squared, which means h is going to be close to sqrt of n. And that was the whole trick, because when you are trying all these possible heights, you will always reach at most sqrt of n, right? You can do something like try the height, try 1, 2, 3, dot 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 until you get to the greatest one such that this formula is less or equal than n, right? Let's call it max h. And after you have found max h, so you know what is going to be the maximum height of some pyramid, you will start now from max h but go in the opposite direction, right? You know max h, you decrease from n this formula for max h, then you are left with another n, n1, which is way less than n. So you have to find the next max h, and now you can just move backwards in order to find the max h, right? By doing this and not always finding again from the bottom the new max h, what you're gonna have here is basically 2 crossed max h iterations, right? Which is pretty cool. So you found max h, you know this is the greatest one, and then move backwards. 2 crossed max h, but again, let's not forget that h is almost, the max h actually is going to be close to sqrt of n. So you have something like sqrt of n total iterations. And because the sum of n was really small or something, you basically could have done it too. So yeah. Yeah, there's a guy who spams with C. Dude, that's not cool. And yeah, I have already explained C, man. So wait for the live to be again streamed, not streamed, anyways, to be rendered and then stored on YouTube basically, and you're gonna see me explain C again. So this was it, guys. I'm very sorry because the round was unrated, unfortunately, but that's life. We had fun, and I for sure am going to find out what is wrong with my D, and of course upsolve E. So I'm gonna see you the next round. Again, if you haven't by now, subscribe, like, and support the channel, man. If you haven't subscribed yet, join the party. Come on, it's not that hard. And we will keep the tradition of doing these live streams after each and every Codeforces round that I compete in. Let's hope that each and every Codeforces round ever, even after 100 years for now, who knows, we'll see. So again, subscribe to the channel, like, support the videos, and I'm gonna see you again after the next Codeforces round. That was it. Bye guys, have fun and keep hustling.